Hello everyone, I am Dr. Nitin Kumar Saxena. In this video, we will discuss the concept of electric current. So, to understand the concept of electric current, if you refer my previous videos in which we have discussed the property of electric charge when it is placed at some place, it is placed stationary, it is static, it has no motion. So we say when charges are stationary, the study refers to electrostatic charge. Now what happens if this charge particles moves, right? So I'm saying, okay, if any body or in any matter, suppose this is a matter, and for this matter, if I'm talking about this matter, suppose I am saying total plus q charge is going from surface A to surface B, right? So we have a matter may be of any shape. Let us, I am saying this is something like this, cuboid shape. So what will happen? So you see what will happen here. From the surface A to surface B, I am supposing plus q charge particles are moving from surface A to B, and at the same time minus q charge particles are moving from B to A. So at any time we can say yes, the q net will be q minus q. Okay, so this means overall either from A to from A to B, charge particles will move, net charge particles, maybe positive charge particles, or from B to A, negative particle will move as a resultant of the charge. So at any point we can say that net charge is given by the sum of positive charge and negative charge, and in that way the current is a constant which is defined as I is q upon t. Means we will see that from any surface in unit time how many charged particles are moving, and hence electric current can be defined as the charge per unit time. So what we can say here that it is defined as the movement of charged particle per unit time. Okay, so charge particle moving per unit time is defined as your current. This is I is q upon t. If I want to see a charge particle for a small time interval, so I can write this expression like del q over del t, right, where limit del t approaches to 0. This means what I am doing, I am reducing the time. Suppose I am saying okay, from this is time, so I want to see from time this t1 to time t2 how many charged particles are moving. This is q, so t. So if I am going to reduce this time, so this will convert into del t, and for this del t small, this is called incremental change. And incremental change we can define I as limit del t approaches to 0, del q over del t. And this thing can be further defined as, so here this can be further defined as I is dq upon dt. This is what? This is dq upon dt is what? Change in charge with respect to time. So I is also defined as change in charge with respect to change in time. Okay, so we can define I either by this definition or by this definition. Now the second concept is what will be the unit of charge, unit of current. So you see the unit of current is defined as, if you see from here, so this is coulomb per second, or in short it is defined as ampere. Okay, so the unit of current is ampere, which is equal to coulomb per second. From here you can see coulomb per second. So in short we defined it as a ampere. Now you see this A may vary from even microampere to mega ampere. Okay, so the range of current goes from, suppose the minimum the value may go from, or may be more less than this also is possible, less also possible. Okay, less also possible. Similarly, more 10 to the power 6 may more also possible. But for the practical conditions, the current can go from microampere level to mega ampere level or kilo ampere level. Normally, we say mega ampere level or kilo ampere level. If you see kilo ampere level, right? Kilo means 10 to the power 3. So, what are the examples when the current will be in the range of kiloampere or in the range of microampere? You have seen the thundering conditions of the clouds. When there is a storm, the clouds strike with each other, they produces lightning, and this lightning has the charged particles which, when the two clouds strike, they release charged particles, and these charged particles move towards the earth, because normally we suppose that earth is negatively charged. So when charged particles are produced by the clouds, they suddenly, instantaneously moves towards the earth, and since the charged particles are moving from cloud to earth, this means charge is in movement, and if charge is in movement, what they will produce? They will produce a current. And in this case, the the range of the current goes in kiloamperes, very high current, right? At the same time, if we are talking about our body, we have nerve systems. So in nerve systems, there is also charged particles moves. Like if you all know that our body has a circulation of blood, and when blood moves in our body, this means charged particles are moving in our body. And this charged particles, since moving, they also produce current in our body. And this current, which is in our nerve system, is in the range of microampere. Okay, so the range of the current may go from this small value to high value. Okay, and in between, for different applications, different range of amperes, different range of currents are possible. So let us see. This is the general concept of electric current. Now what happens if we have a current conductor? So what will happen? electric currents in conductors. We know that every conductor or we say any matter has molecules in it, and every molecule has atom in it. An atom again can be divided in the portion of nucleus having the positive charge, and electrons are moving around the nucleus. So this is the basic structure of any matter. If we are talking about conductor, so the basic structure of conductor. So for this case, if I am saying that, for example, you all know the Avogadro number. Avogadro number gives the value of molecules in per gram is 10 to the power 22 right? Molecules. So this means if a gram has 10 raised to the power 22 molecules, this means there are enormous molecules in a matter or in a conductor, and every molecule has atoms and every atom has electrons, right? And these electrons are free to move from one place to another place inside the matter. Okay, so this is the concept of conductor, that in conductor normally, if I am saying this is a conductor of cylindrical shape, right? So it has atoms, means it has conductors. This is conductor, so conductor has molecules. Every molecule has atoms, and every atom has electrons as well as neutrons. So normally what happens, if this has electrons which is moving across the nucleus and the whole configuration makes atom, so these electrons are inside the conductor free to move. Okay, so if they are free to move, so this means we have the charged particles which are moving, right? Now what happens if we are talking about the conductors? So we can say that yes, normally conductors may be of two types, metal type or electrolyte type, right? What is the difference between metal type conductors or electrolyte type conductors? That in metal type conductors, we assume movement of electrons. Okay, we assume that electrons are moving. Like if electrons are moving, naturally the protons or positive nuclei are in the background, right? But normally we consider that electrons are moving. While when we are talking about the electrolyte, so in electrolyte what happens? Negative charge, negative and positive, both moves. Okay, both move. Both move. Okay, so the concept is, when we say yes, if I am saying electrons are moving in this direction, right? So in this conductor, electrons are moving from, suppose this is A, this is B. So movement of electron is from A to B. So the direction of the current is from B to A. Okay, so this means we assume that the direction of the current is opposite to the movement of the negative charge particle. And what are the negative charge particle? Electrons. So if electrons are moving from A to A, the direction of the current will be this, right? So this will be the direction of the current if electron is moving in this direction. So what we can conclude? We can conclude that yes, charge, if positive charge are moving, then current direction is same as the positive charge direction. If negative charge are moving, then direction of the current is opposite to the negative charge. So if we have considering, it does not mean that only the positive charge particle or negative charge particle are moving, but we are considering one as a main, other as at background. So in any conductor, if we are saying that yes, electrons are moving normally, since we know that in conductors electrons are easily moved from one place to another place. So normally what we say that yes, electrons are moving. So if I am saying if electrons are moving like this, so or like this, so if I am saying electrons are moving like this, so this is the direction of current, here this is the direction of current, this is the direction of current, and here. Okay, so always the direction of current is taken in opposite to the direction of the electrons or negative charge, right? Normally what happens, if I assume any metal or metal conductor, suppose I am saying yes, this is your metal conductor, and this metal conductor has so many electrons. So this metal conductor has so many electrons. So what will happen, since I told you that electrons are free to move inside the conductor, they cannot come outside of this conductor, but they are free to move in the structure of this metal. And what is this metal? Conductor. So if electrons are free to move, so what will happen? They have the random motion. What does this mean? This means maybe this, if there is initially no electric field. Okay, I am talking there is no electric field. So if there is no electric field, so what will happen? There are positively charged nucleus, negatively charged electrons. So some will, like on this electron, if I am talking, some nucleus will provide attraction force, electrons will provide the repulsion force. So as a result, the electron has the force in random direction. Maybe like this, here maybe like this, or something like this. So any okay, like this also. So you see, I told you that any material, any conductor has millions, trillions, like not million, trillions is a very small word. I told you that Avogadro number is 10 to the power 22 for 1 gram. So 1 gram has this Avogadro number equal to this molecules, and if 1 gram has this molecule, so you can imagine the number of electrons in this metal conductor. So if all the electrons are moving in random direction, so what will happen? There will be no specified or specific direction for electron. So there is no specific direction for electron movement, and as a result the overall charge movement is 0. And since overall charge movement is 0, therefore I will be 0. And hence, we can say if we are not providing any electric field to the conductor, the charged particles, the electrons will move, but they will be in random motion. And since they are in random motion, so there will be no overall net charge movement, and as a result there is no current. And hence we can conclude that if no electric field is applied across conductor, the charged particles will be in random motion. So net charge movement will be 0, right? And therefore net current will be 0. So this is the condition when we say we are having no electric field across the conductor. Now what will happen if we are providing some electric field, right? Suppose I am saying I have this conductor. Okay. I am having this conductor. Right? So if I am having this conductor and I am saying, yes, on this conductor we have two surfaces, suppose surface A and surface B. Initially we are providing plus Q charge here and minus Q charge here, right? So what we are providing? Initially we are providing some charge particle at surface A and some charge particle at surface B. You can imagine that, okay, we are like putting two discs, one disc here, one disc here. This disc is positively charged and this disc is negatively charged. So when we are providing this disc, right, and when we are providing this disc, and this is positively charged, this is negatively charged. So what will happen? Since this is positively and negatively charged, so there will be a movement of charge, and the movement will be continuously occur till all the positive charge and negative charge will combine and make the system neutral, means no charge, because this is conductor, and in conductor the flow of charged particle is possible. This is different condition from the capacitor. In capacitor you also have plus Q minus Q, but the charged particles cannot move. But here we have conductor, so the charged particle can move. So if charged particle can move, the charged particle will move till there is no resultant charge. And hence we can say the current will flow for the small interval. The current will flow till there are charged particles moving from one surface to another surface. Once all the charged particles provided at this surface or this surface have moved, after that there is no movement of charged particle and hence there will be no current. Okay, but if I am having something like this, and I'm saying okay, I'm continuously providing the this is the voltage source, and this voltage source is continuously providing the charge particles to this conductor. So what will happen? Since this is providing a continuous charge particles, right? So there will be a continuous current flow in this conductor, right? Hence we can say, if we are providing a constant source means it has some amount of charge and they will flow, and after that the charges will be zero. So what will happen? In that case, current will flow for instant of time, and after that there will be no flow of current. Suppose for understanding this, again I am saying okay, this is conductor 1 and this is conductor 2. Here I am connecting this conductor with voltage source, and here I am connecting with this capacitor. Okay, both are the conductors. So in first case, capacitor has the fixed value of charge, and once the circuit is complete, suppose I am saying here I am a switch S. So what will happen when I will switch on the circuit? This charge particle will start to flow, and since this charge particle will start to flow, what will happen? The current will start to flow. But after some time, the charge on capacitor will become to 0, and there is no further charge to flow. And what will happen then? Then this means when all charge particles have flow, so current will stop to flow, and after some time there will be no current in this circuit. But if I see this circuit, this voltage source has a property that it will provide you continuous charge, and since it is providing a continuous charge, so what will happen? There will be a constant continuous value of the current. Is it clear? Right? Now the question can come in your mind, if this charge particles are moving from here going to the conductor, and after some time there is no current. So what is going on here? So you can understand it that when the current flows in any conductor, so it will dissipate the energy. As I told you that, yes, here we have electrons, right? Because of this charge particle, they will start to flow, and when they will flow, they will strike with each another, and when they will strike with each another, they will reduce their energy in the form of heat. So what will happen? The energy which is supplied in either this or this, so we are giving the energy from here also. So this energy is lost in the form of heat. Why? Because the electrons inside the conductors have some motion. When they have some motion, they will strike with other electrons and nucleus, and when they will strike, they will release the energy in the form of heat. And hence, whatever the energy is given in case 1 or in case 2, that will go in the surroundings, in the environment, through the in the form of heat, and hence we can say the energy will remain conserved. Where whatever energy we are giving here, that energy is going out in the form of heat, right? So in this way we can understand that how the conductor behaves. So conductor behaves in 2 cases, even in 3 cases. Number 1, when there is no electric field. Number 2, when there is electric field but the fixed amount charge are having the circuit, and after that there is no charge. And third case, a continuous charge can be given to the conductor. Okay, so let me conclude this. So I can conclude like this. Yes, that conductor number 1, no electric field. So when we have no electric field, so no current, only random motion. Number 2, electric field with fixed charge value. So current will flow for some duration. And last, electric field with continuous flow of charge. So current will also flow continuously. Okay, so I hope all the 3 cases are clear to you how the current flows inside the conductor, and let us move to the next topic. The next topic is Ohm's law. Okay, so according to Ohm's law, Ohm's is a name of a physician who gave this law, and hence this law is known as Ohm's law. So according to the Ohm's law, we have seen that when we have given the voltage source to any conductor, so what will happen? Since we are giving the voltage source, this means we are providing some electric field, charges from this to conductor, and hence since the charge can flow, the current will start to flow in this conductor. And you see, if we have more value of V, this implies more charge will flow. If more charge will flow, this implies more current will be here, right? So we can conclude in this way that yes, our V is proportional to I. Our V is proportional to I. Means if we are providing more potential, more voltage, the current will flow more. If we are providing less voltage, the current will flow less. And this is given by V equals to IR. This means this relation is known as Ohm's law. So what is Ohm's law? In any material, in any conductor, the voltage supplied is directly proportional to the current. And if we give a constant, then this constant is R. So R is called resistance of the material, right? Normally its unit is ohm on the name of the scientist, and this is denoted by this symbol. And if we find R, this will be V upon Y, so this will be volt per ampere. So the unit of resistance is ohm. and this is denoted by this symbol, right? So this is the basic definition of Ohm's law, that the potential is directly proportional to the current. More current, more voltage, more voltage, more current, less voltage, less current, and hence this relation is given by V equals to IR. Now let us try how this R vary, or what are the factors on which this R depends. Because you see, this R is a property of this conductor. R is the property of conductor, right? The property of the conductor material, as well as the shape. Okay, so this R depends on the property of the material and the shape. So to understand how it will depend, let's see. A case, suppose I am having this conductor of length L and area A, right? So area A means this is something like this. Okay, so if this is something like this, so this area is A and this length is L, right? Now what I am doing, I am taking the two conductors, same material, and same dimension. Means the same as, again I am taking the another one with same material and with same length and area, and now I am putting both the conductors, number one in this way, and in second case I am putting in this way, right? So you see, and if you see first case, if I am saying this is V, this is I, so what is the relation here? If I am saying yes, this resistance of this material is R, so V is equals to IR for first case, right? Now you see what will happen here. If I am putting the two materials like this, so the charge produced by this voltage source will move here, right? So first the charge will go in this, and then the charge will go in this, right? So this means the charge particles which are moving from this voltage source will go in this and this, so their movement will be like this. Okay, but here what will happen, the charge particles which are coming from here, they will go in this and also in this. So what is the difference? You see here, the charge particles here will be half, while what will happen here, the charge particle will be double, because the charge is from here, while here charges will move like this. Okay, so what we can say, in first case, this means what will happen, we can say that in first case we are changing the length of conductor. In second case, we are changing the area of conductor, right? And hence when we are changing the length and area of the conductor, the relation will also change. And how it will change? It will change that yes, our R, here you can say in first case, R will be depending on the length, directly proportional to length, and inversely proportional to area. Okay, so this means, because what is R? R is V upon I. Right? So we can say from this that yes, resistance depends on the length as well as on the area. If we are changing the area, the overall resistance will change, because now the charged particle will flow from this surface to this surface, right? And here the charged particle will flow from the same surface, but they have to travel more length, right? They have to travel more length. Here the length is same, but they have more area to flow, right? So in this case we can conclude that R is proportional to L here and R is proportional to 1 upon A here. So R is given by rho L upon A, where rho is a constant which is known as resistivity of material. So whatever material we are using, every material has some property, and this property is called resistivity of the material. And in short, we can say yes, R is given by the formula rho is L upon A, and hence since I wrote here that R is the property of the material as well as the shape, so you see R depends on the shape L and A, and R depend on the rho. Rho is what? Property of the material. So this means we can write here, yes, the R is given by rho L upon A. So what is the value of V is? IR. So when you will put here I rho L upon A, right? In my previous video, I have discussed the concept of current density. So if we know the current for unit area, then current density is defined as I upon A, right? So if I am denoting the current density by J, so what is J? J is I upon A, means ampere per meter square. This is the unit of J. J is what? Current density. So what I am saying? I am saying the current density is defined as I upon A. So if I put here, so what I will get? I will get V is I upon A, you see I upon A rho L. So what I will get? I will get V equals to J rho L. Right. Now, from the concept of electric field intensity, you know the relation that E into D, or E into D is given by B. Right. So what is D here? D means we have this conductor having area A, maybe of this shape or maybe of this shape, that does not matter, with length L, with rho the specific resistance. So I can take any shape. Okay, so you see here, if I am providing the voltage between these two surfaces, right? So an electric field will be developed at these two surfaces, and this electric field E into the length between these two surfaces L, so EL can be given by V, and hence in place of V, what can I write here? EL. So what will happen? EL is J rho L. So what I will get? I will get E equals to rho J. Okay. Now you know that E is a vector quantity. Electric field has its direction from positive charge to negative charge, and J is also a vector quantity. If current is flowing in this direction, so the surface perpendicular to this is called the direction of the J, and hence what can I do now? I can write like this: E is rho J in vector form. Okay, so this is the relation. This is the relation between the electric field and J. Again, if I want, then I can write rho is 1 upon sigma, or sigma is 1 upon rho. I am introducing a new parameter. So what is new parameter? This parameter sigma is called conductivity of the material. Okay, conductivity of the material. So if I put the value of sigma here, so what I will get? I will get J equals to sigma. Okay, so you see, either you can write Ohm's law. This is very interesting, that this is the most general method, most general way to define the Ohm's law. V equals to IR. But Ohm's law can also be defined or can also be represented by this formula, or finally from this formula. So this is also a very popular formula. J equals to sigma E, where J is current density and E is the electric field intensity and sigma is the conductivity. Okay, so Ohm's law can be represented either in this form or in this form, or the popular vector form J equals to sigma E. If you refer any standard book, you will get the Ohm's law either in this form or in this form. So this is something which we are relating in the form of vectors. J equals to sigma E. One more important thing is, or interesting thing is, you see here that your formula is sigma is 1 upon rho, right? Rho is defined as resistivity, while sigma is defined as conductivity, and both are inverse to each other. Both are inverse to each other. This means if a material has more value of resistivity, the conductivity will be less, and vice versa. If resistivity is less, then conductivity will be more, right? Resistivity is the resistance which oppose the flow of current, while conductivity supports the flow of current. So in this way we can say that if current is moving, so conductivity is a parameter which supports the flow of current. Resistivity is a parameter which opposes the flow of current. So this means a material having more value of resistivity means they are having the more oppose for the flow of current, and if a material has more value of conductivity, this means it will support the flow of current. Hence, the hence, what can we conclude? Conductor must have more value conductivity and less value of resistivity. Okay, so if you having the, like, I'm giving you an example. Okay, you have two materials A and B and sigma and rho. So I'm saying that, suppose for example this is 10, this is 20. So which is a good conductor? B is a good conductor. Suppose I am saying another example. This is 100, this is 60. So which one is a good conductor? A is a good conductor. So by the value of resistivity and conductivity, you can find the better conductor, and that better conductor you can use in various applications. Ideally, if anyone asks for ideal conductor, what will happen? If we have ideal conductor, so ideal conductor must have the full support of flow of electrons. Full support of flow of electrons can be defined as that the value of sigma should be infinite and the value of rho resistivity should be 0. So this may be a good question that anyone can ask you, that what are the conductivity for ideal conductor? Infinite. What are the conductivity, resistivity for ideal conductor? 0. So I hope the concept of Ohm's law is also clear to you. In this video I stop at this point. In next video we will discuss the another concepts related with electric current. Thank you very much.